This is the third video lecture about lexical analysis, and it's an oddly titled one called Regular Expressions are Trees. So what do I mean by that? Well, for now, you've looked at regular expressions with the definition. You're familiar with it. I'm sure you've used it for lots of different applications before, like searching, etc. So at this point, I think you'll be like this person here saying, everybody stand back. I know regular expressions. And then swings in like Tarzan and types in some lines of Perl and then swings off, and people are cheering over here. You might think, well, you mastered regular expressions, but what we've done so far is actually learn how to use regular expressions and use them effectively, how the matching works. But we still haven't learned how internally you can take a regular expression and then match strings with it. Like, how do you actually implement what's inside of Lex? So that's what we're going to look at next. So everything you need to know to do lexical analysis, you kind of already know, like how to use Lex as a tool. But what you don't know yet is how Lex is built. Like, how did people write Lex? The notion of using Perl here is kind of interesting because Perl is a programming language that was built around an efficient implementation of regular expressions. Regular expressions are ambiguous, as you might have realized while using them. So if I have an input regular expression, AC or BC, there are many different ways to interpret that regular expression. So for example, depending on where you put brackets or how the operators are applied. So as you can see, there are two operators here. There is a concatenation between A and C, another concatenation here, and then we have this OR in the middle here, right? So we have these three operators. Depending on what those operators are taking as arguments, you can get different interpretations of this regular expression. So in the first case, you would have the concatenation operating between A and C, right? And then the alternation is happening between A, C, or B. And then you follow that with the concatenation with C. So you can see that order of operations is portrayed using these parentheses, the grouping of which operator happens first and which operator happens after that, and so on. So that's one option. You concatenate A and C, you alternate with B, and then concatenate with C. That's not the only way you could organize these operators. So you could have C or B and then concatenate it with C and then concatenate with A. You could concatenate BC together, alternate with C, and then concatenate with an A. And this one is doing the alternation in the middle, C or B, and then concatenate with A and C, right? Finally, we have one where you do the concatenations first, and then you alternate between the two concatenations. So that's what is happening over here. All right, so if you notice these two, you will notice that there is some similarity between them. And the similarity here comes from the fact that if I have two concatenations happening, the concatenations can be reordered. So for example, if I had a regular expression A, B, C, I could do these concatenations in different ways. I can do A, B first and then concatenate with C, or I could concatenate B and C first. And these are equivalent because the order concatenation is commutative, which means that the order doesn't matter, right? And that's exactly what's happening in these two. If you compare these two regular expressions over here, you can see that it's almost the same. The only difference is that the order of operations is different. Okay, so how do I choose between these five? Well, we use operator precedence rules and, as we'll see, associativity rules in order to pick which of these different bracketings is the right bracketing for a regular expression. And this is just by convention and by analogy to how we are used to using these operators in math. So if we assume concatenation looks like multiplication and alternation looks like addition, then you could think of this as 2 times 3 plus 3 times 5, in which case you know that we would do the multiplication first. And that's why we prefer to write the regular expression or interpret the regular expression using that bracketing at the last one there in the list. So what are these precedence rules? Well, the first precedence rule is you always group using parentheses. The parentheses always win. So that's why when we show you the exact precedence, we use brackets to show it, right? So we are using these brackets here in order to specify the precedence because parentheses has priority over everything else. The second priority is for the unary operator, star. It doesn't appear in this example regular expression, but we'll see other examples later. And then there's a binary operator for concatenation. That's the third priority. And the fourth priority is binary operator for alternations. So we apply these precedence rules in order. So we look at this list of operator precedence rule and always use the operation that's of higher priority first, which is why the correct bracketing based on these precedence rule is the one marked here with the star. Okay, in order to check your understanding of this topic, I have a few questions for you to consider. So one question might be, can you look at the strings accepted by these different regular expressions and use that information somehow to discover the precedence rule? So let's assume that you don't know what these precedence rules are and you want to discover these precedence rules for yourself. You could first take the input regular expression, expand it out to all of the different bracketings you can get. So in this case, there are 5 bracketings you can get for this input string. And then you can notice that some of these bracketings will recognize a string that the others don't. So obviously the ones that are marked here with the triangle, these have to accept the same strings because they are equivalent. But the others do not, right? So if I look at here in this example, this regular expression over here, does it accept the string AC? You can see that it does. So you can see that A can be followed by C, but it also accepts the string ABC. This is accepted, but this is accepted as well. Whereas if you consider this string, the one that's winning, does this recognize ABC? You can see that it cannot, right? So there's strings that can be used to distinguish which regular expression bracketing is being used by the implementation. So we know that almost every regular expression implementation uses these operator precedence rules. So we already know what the right bracketing is, but could you discover these precedence rules by using a string to probe each of these regular expressions? The hint here is to compare matchings on input strings and these 5 unambiguous regular expressions for the original regular expression here. Another question for you is how many possible trees can you write down which are explicitly bracketed for the regular expression AB star or C star? We've seen that regular expressions can be bracketed explicitly, but I can actually take this bracketing and show this bracketing as a tree structure. So when I have the same irregular expression I had in the previous slide, and I have AC concatenation first, BC first, I can represent that in this subtree over here. The bracketings just correspond to a tree structure. The bracketing is a tree structure, it's just another notation for it. Similarly, if I have A star star, this is the tree structure for A star, and then I'm applying a star on top of that. So the bracketing and the tree structure, as you can see, are equivalent. And finally, if I have the ambiguous case where it's ABC can be bracketed 2 ways, right? And it could be ABC or ABC. We use left associativity to get a unique tree out of it. So that's why we bracket the left concatenation first and then the right one. So both alternation and concatenation are commutative. So we use left associativity to get a unique tree. The question for you here is to provide an unambiguous bracketed tree for the regular expression A, B star over C star using these precedence and associativity rules, and to show the tree structure for it, right? So you want to draw out the tree just like I've done here. Another useful thing in writing regular expressions is to know that regular expressions some of them can be equivalent to each other. In fact, some of them might be simpler versions of more complex regular expressions. And this is useful when you're writing regular expressions in your lexical analyzer, for example. You don't want it to be very convoluted, so you want it to be readable by humans. So let's look at this question. I want to show that is this regular expression on the left-hand side of the equal, is it equivalent to this right-hand side? So on the face of it, looks like quite complicated. But you can actually take these regular expression strings and treat them like programs and look at whether these two programs are equivalent. They're equivalent if they accept the same set of strings. But we can also look at it syntactically. So I can take advantage of the fact that the operations are commutative and say that these different ways of writing the regular expressions are equivalent, right? It doesn't matter which order is the concatenation. It doesn't matter which order is the alternation. So we can see that these two regular expressions, R, S, and T stand for arbitrary regular expressions. We know that they're equivalent. Similarly, we can say that when we have an alternation and a concatenation, we can actually distribute it. So we can factor into the bracket the concatenation so that the T here is being concatenated into the alternation, right? So this is very similar to what we could do with multiplication and addition. Again, the analogy works here. Another thing you can do is to say that, well, certain things are redundant, right? So if you end up with a alternation between two regular expressions that are identical, then you don't really need two copies of that regular expression. You can just replace it with one. Similarly, if you end up with an empty string, then that's the same thing as R without the empty string. The other sequence of equivalences are to do with the closure property, the star operator. You can see that I can repeat the stars and it has kind of essentially no effect, right? So you can take R star, and replace it with R star star, and that can be further simplified into just R star. 0 or more repetitions of R, and there's many different ways to write that down as a regular expression, and they're all equal. We can also take the sequence and re-bracket it. So you can reorder the bracketing of this sequence of regular expressions. So let me use one of these as an example. So here, if I have RS star followed by R, I know that RS can be empty, right? So this RS star means it could be empty, or you could have a single RS followed by R, or you can have two RS followed by R, and you can have three RS followed by R, and so on. And we know that these are the only kinds of matchings you can get with this regular expression. So if you look at this a little bit sort of carefully, you can see that I could bracket this SR over here, I could bracket this SR, and this SR over here. So I'm just reordering the bracketing here. And now I can get R followed by SR star. You can see that that's exactly what I have here. So the rebracketing kind of works to give me this equivalence, and that's tremendously useful. Okay, so let's look at this, this case over here and sort of examine it. Can we sort of reason about this equivalence in some way? One way to reason about the equivalence between these two regular expressions over here, the left, is this left equal to this right hand side, is to view it sort of and reason about it a little bit graphically. So we can take this alternation. So this is the left part of the regular expression, and I'm splitting it between the two parts of the alternation. So this is two parts. And you can see that this part here, this one, corresponds to this group 1 over here, and this part over here corresponds to this group 3 over here. Now, group 1 itself can be split up into a part that's in the middle here, this 1, 0 star, and that's sort of a smaller part of group 1, which is this group 2 here, right? So let's examine this this part, this group 1 here, and see the structure of it. So you can see there's a 0, and then there is a 1, 0 star, and then there is a 1. If this 1, 0 star, this can be the empty string. So what we are left with, if this is empty, is the string 0, 1, right? Because this middle part over here, this middle part goes away. Or I could repeat it once, or I could repeat it twice, and I could repeat it 3 times, and so on, right? So I could keep going. Now, the interesting thing about these repetitions over here is that I can re-bracket them, right? So I can think of this as 0, 1 followed by a 0, 1, and I can think of this as 3 0 1s, one after the other, and so on. So you can see that essentially I have in the left hand side 0, 1 should happen once, or it can happen 0 more times after that. Now it looks very similar to this right hand side over here, this group, this regular expression, which is 0, 1 star, because now I have 0, 1 followed by 0, 1 star. Now if you look at 3, it says it can be 0, 1 star. So if I put an alternation back over here, it's or 0, 1 star. And you can see that if the right hand side on this side of the alternation can accept the empty string, then there is really no need to sort of insist on a 0, 1. So this whole thing can reduce down to 0, 1 star. So this is one way to reason about it. Another way to reason about it is by just using those equivalences purely syntactically that we saw before. So let's look at, again, looking at the same example. We want to simplify this complex regular expression. So we'll start with looking at a substring of this, which is 1, 0 star 1, and look for some equivalence that we can apply. So we find among that list of equivalents of regular expressions I showed you, we have rs star r, and you can see it matches over here, because this, if I write it down, you can see it exactly matches that pattern. And I can replace it with the right hand side, where again I'm just doing that re-bracketing trick. So I replace it with 1 followed by 0, 1 star. And now you can see that this 0, 1 over here can be bracketed by using this equivalence. So I end up with 0, 1 followed by 0, 1 star. And I can take that and replace that with, so that's just r star, right? And then I can replace it with r plus. And if I have an r plus followed by a 0, 1 star, we know that just from the reasoning we saw from the previous slide, we can see that r plus or r star is just r star followed by r star, and this can be replaced with r star, which gives us finally this much simplified regular expression 0, 1 star. As a question for you to try out, try to show that this regular expression over here, 1 followed by an alternation of 0 or 0, 1 star, is equivalent to this. So this left-hand side is equivalent to this right-hand side. Use the same kind of idea. You can use these equivalences from the previous slides in order to show the answer to this question.